Okay, hello everybody. Looks like our participants are trickling in. I'm going to give it about 2 more minutes and we will get started with our program. Okay, we'll go ahead and get started. I hope everyone is having a wonderful Wednesday and you are enjoying Black Space Week 2024 so far. I am super excited for today's session. I am Nia Butler-Craig, the Aerospace Chair of Black In Astro, and I will be the session's moderator for the day. But I'm very excited to hear from all of our brilliant grad students in Black In Astro. So without further ado, I will start with the judge introduction. So we are honored to be joined by Dr. Cadence Payne, Dr. John Hood, and Dr. Carl Fields, who will be our Graduate Research Showcase judges. I will start off by introducing Dr. Payne. She's an aerospace engineer with a PhD from MIT's Aero Astro program. Her research focuses on technology development for small spacecrafts called CubeSats that observe the Earth. Her current projects involve CubeSats that probe radio frequency emission from the Earth's aurora, as well as missions that provide data for climate and weather monitoring via ocean observations. Her ultimate goal is performing meaningful work in the aerospace industry to support climate change mitigation techniques. Cadence is also a co-founder of Aero Astro's Aero Afro, former president of ACME, and former co-events chair for the Black Graduate Student Association. So thank you, Dr. Payne, for joining us today. Moving on to Dr. John Hood. Dr. John Hood grew up in Columbus, Georgia, and is the youngest of 10 siblings. He attended Columbus State University, where he received his BS degree in astrophysics and planetary geology, with minors in physics, geology, and robotics. With his focus on astronomy, he applied to and was accepted by Fisk University in the Fisk Vanderbilt Master's to PhD Bridge program, where he received his MA degree in physics, where his thesis research was the search for orphan flares via multi-waveband observations of Fermi bright blazars. Wow. Shortly thereafter, Dr. Hood was accepted into the PhD program at Vanderbilt University. One of the highlights of his studies was being named a part of the South Pole Telescope Group. That group built and installed a telescope at the South Pole. After being awarded his PhD, his dissertation title was CMB Experiments as AGN Monitors. Dr. Hood was selected as a National Science Foundation Fellow with the Office of Polar Programs for a postdoctoral fellowship, where he is currently working on deploying the Straw Hat catalog of millimeter wavelength bright AGN at the University of Chicago. Wow, a lot of brilliance. Moving on to our last judge, but last but not least, of course, Dr. Carl Fields earned his BS in physics and Earth and space exploration, astrophysics from the Arizona State University in 2016. His PhD is in astronomy and astrophysics from Michigan State University, which he earned in 2021. Carl is a computational astrophysicist broadly interested in massive stars, their explosions, and the multi-messenger signals they produce. In 2021, Carl was named to the Forbes 30 Under 30 for Science list, and from 2021 to 2024 held the Feynman, excuse me if I did not pronounce that properly, the Feynman Distinguished Postdoctoral Fellowship in Theory and Computing at Los Alamos National Lab. In fall of 2024, Dr. Field will begin as an assistant professor, assistant astronomer at the University of Arizona Department of Astronomy and Steward Observatory. Thank you so much to our judges for not only lending your time, but your expertise to us for Black Space Week and for our graduate research showcase. I did want to give the opportunity to for any of the judges to share a couple words if needed, or if they'd like to, or at least wave to the camera so we know who you are. There's Dr. Hood, there's Dr. Payne.
Sorry, everyone, I don't have a camera, but looking forward to hearing about all this great research.
Lovely. Thank you so much.
Very excited to be here and already very proud of you all. So
yes, and just excited to be a part of everything.
Excellent. Thank you all so much for being here with us. So without further ado, excuse my my little speech slips, I will start with our first presenter. Her name is Kayla McGowan. She is from Vanderbilt University. And a research overview that she provided us was that her goal is to improve LIGO sensitivity. They investigate scattering surfaces to reduce the scattered light effect. There are at least 2 known populations of scattering noise. They investigate the multiple origins of one population by implementing an algorithm that uses a witness channel and scattering event time identified by the Gravity Spy machine learning tool. The algorithm filters noise and calculates properties of the arches, including velocity, to trace the scattering noise surface. Using this algorithm, they investigate changes in scattered light properties like frequency, velocity, duration, and rate during O3 compared to O4 after upgrades. They find the number of scattered light occurrences has decreased at LIGO Livingston Observatory in O4, but shape and duration changed, indicating a change in origins from the previous run. So I probably butchered that. So I'm extremely excited to hear from Kayla about her research. Please, whenever you're ready, start sharing and begin your presentation. Okay, doesn't look like we have Kayla on at the moment. So I will go ahead and move on for now. 1 second. Okay, let me confirm. I do see Victor. Victor, do you mind going first? Okay. I do see him on here, so I'll go ahead and introduce.
Hi, Naya.
Hi, Victor. Okay, so you'll be our
Yeah.
first presenter. I apologize for the confusion. So to give his
Yeah.
research overview, the YMIR mission, Enceladus biosignatures detection mission. Here they propose to use instruments such as Raman spectroscopy, E-Themis UV fluorescent spectroscopy, and light field volume fluorescent imager to determine if hydrothermal vents on Enceladus have chemicals that can help life grow and develop like those on Earth. Their mission goal is landing on the south pole of Enceladus, studying the composition and location of plumes, looking for biosignatures, and comparing them to, okay, I'm not even going to try that one, but that. The mission architecture is a 4-leaf clover rover design with each leaf detachable from the base. The leaves are connected to the base via tethers. So without further ado, I will allow you to start sharing and present your work with us. Check it in, Victor. Okay. We're going to roll with the punches. Victor, can you hear us? Okay, it looks like we lost Victor. Okay. One moment, everybody. Let's see. We will start with, Andrea, are you ready to present?
Yeah, I'm ready. Can you hear me? I'm in a windy location.
No problem. Yes, we can hear you.
No problem.
Okay.
Perfect.
I'm
give
gonna
me
go
one-
ahead and let. Okay.
Perfect. Give me 1 second. Let me just. Sorry. All right, I'm ready. I can start my video. I am outside. I apologize, and it's windy. I'm in the windy city.
No problem.
Thank you guys for having me. Okay, here are my. Uh-oh, I don't know if it is the wrong slides. I just had them up. 1 second. Here they are. All right, I will share my screen. This screen, PowerPoint. There it is. Can you guys see my screen? I don't know what's going on. Okay. Okay. Is it? Can people see?
Yes, we can see it fine.
Okay, great. All right, 1 second. I'll just. Okay. Great. So, I guess this timing starting out. I apologize for the horns. I hope you can't hear that. All right. So, hi. My name is Andrea Bryant, and thank you all for having me. I study for my thesis. I study hypothetical icy moon seismic profiles for comparisons to future seismic data. And so during this time, I'm just going to give an overview of some thesis work. And I'll start with just talking about the main focus of my dissertation work, which has been Titan. So, all right, Titan is Saturn's largest moon, and it is of much interest within the solar system because it has a thick atmosphere of nitrogen and a lot of methane. The surface is about 94 Kelvin. And so a little bit ago, about 20 years ago, we learned from Cassini, the Cassini mission, all about Titan. There are many, many flybys, and we learned that there is an ocean underneath a thick shell of ice. And we also saw that Titan is one of the only moons in the solar system that has a thick atmosphere, but that also has liquid on the surface. And in this case, since it's so cold, it's liquid methane. But there's no other moon that has this liquid on the surface. And so because of that, it's of much interest to actually go and explore it. So there is this mission called Dragonfly, which is a NASA-funded mission. And now, thankfully, they now have an official launch date that's going to be in 2028. So we expect to be on Titan in 2020. I think it's 2034, I believe. And there are a number of instruments on this rotorcraft, and it is about the size of a Mini Cooper for scale. And in particular, my research for my thesis has been focused on the seismometer, which is located here. Can people see my cursor? I hope you can see my cursor, but it's here. It's this dome-shaped little seismometer that's created by the Japanese Space Agency, and it's going to be lowered down to the ground, coupled to the ground, left there to measure seismic activity. And then they will fly. They will be raised back up. They can fly around and sample the dirt and all these different things. It's going to be a tremendous mission. We'll learn a lot about Titan, and in particular, my research within Titan seismology is really to create synthetic waveforms to kind of mimic what we will see once we get to Titan. And so, just as seismology has helped us to understand what's going on within the interior of the Earth, we know so much now about the interior of the Earth because of Titan, or because of seismology, rather. In the same way, it's such a useful tool that will help us to constrain the interior structure of Titan. And so the main seismic events that we think we'll see on Titan will be due to tidal flexing, due to the eccentric orbit around Saturn. There could be chiral volcanoes or chiral volcanism events, and then also just in general, this ice, since it's floating on some liquid water, it can actually crack. And these cracking events will propagate syntopseismic waves throughout the interior, and we can actually detect that with the seismometer. And so we will actually be able to more tightly constrain how thick is this ice, which is on top of ocean, and then also what's going on deep within Titan's interior. Some information that we wouldn't otherwise not really know in great detail. We've learned a lot from Cassini, but Titan will really, or Dragonfly will really help us to learn. So next, I'm just gonna briefly now summarize. So I've given a nice background. I hope it's nice. I've done my best to give you a background. So now I'm gonna just talk about now just the work that I've been doing for my thesis, or done for my thesis. So again, seismology is an incredible planetary exploration tool. And so for my thesis, I have created and analyzed synthetic seismograms to study icy ocean worlds like Saturn's moon Titan. And so that this whole process, in a nutshell, starts from taking one-dimensional velocity models. And these are given from data that we have from Cassini. So we can take the gravitational field, we have the moment of the mass of Saturn, sorry, the mass of Titan, also the moment of inertia of the spherical body of Titan, and we can use that to actually propagate a one-dimensional velocity models. This is used. This is created by a code called Planet Profile, and then we can actually take that 1D model, create three-dimensional models within a mesh grid, and this is with a code called AxiSim. And so the first one's open source, you can find on GitHub. This one, AxiSim, I think it's also open source as well. But you probably might need a supercomputer to run this. You need a couple cores, maybe 40 cores would be nice. So where the computer solves the wave equation for specific sources and receivers, and then you get fun stuff. So this is an illustration by a colleague, but in particular, James Tool King at the Jet Propulsion Lab in California. This is particularly the reason why I showed this is because I wanted to illustrate a particular aspect of my research, which are flap rates, which are these methane containing water cages. And so we think that because there's a lot of methane and a whole hydrological cycle on Titan, that there will be a lot of this methane that's been incorporated within the ice shell. And so we should be able to detect these layers with seismology. So that brings me to my next, my key finding number one, and I'm going to present just two here. Key finding number one of my thesis, we have seen, or by we, I have seen, me and my collaborators, mainly Mark Panning at the Jet Propulsion Lab in California, and also Angel Maruziak, who is now at University of Arizona. We found that thermal profile variability drives variable seismic attenuation. So let me unpack that. So by looking at differences in the thermal profiles, and that's like how heat is transported throughout the ice shell, we can see how that directly affects the seismic attenuation. So attenuation is something that if you think of a bell and you were to stuff it with cotton and you hit that bell, that would be kind of give you a clank. So that means that bell will be highly attenuated. That ringing would be attenuated. But if you were to take that cotton ball out of a giant cotton ball for a giant bell, you would see that you would get attenuation. It would be less attenuated. That is reflected in the actual amplitudes here. So we see the less seismic attenuation within pure water ice shells. So we modeled three different models. So we have one that has 10 kilometers of flap rates on top of a 100-kilometer lid. For 20 kilometers, we had 20 kilometers of thick flap rates, and then 80 kilometers of pure ice underneath for this 100-kilometer ice shell. And the third model was this pure water ice shell. And so we see that for pure ice, highest amplitude wave, and this is actually a surface wave called the Rayleigh wave, which I will touch on in the next slide. But we see this really, it's really a pulse. It's you can see this, it's a signature of a floating ice shell. But we see that here. And then for 20 kilometer flap rate, we see something like a little bit more attenuated. So it's a smaller amplitude. And then for this 10 kilometer flap rate, the amplitude is way down here. The peak amplitude of that seismogram is way down here. So, to explain this plot, we're looking at displacement, or this is ground displacement on the x-axis, and we're looking at time, increasing time of the seismic record from 0 to, this is 3600 or 3500. I've cut off the last 2 minutes, or 10 seconds, or 100 seconds rather. This is about an hour. And then I also looked at this as a function of depth. So for deep sources, that's beneath the ocean, we don't see a high amplitude event. But then for shallow sources close, like something like the quake is happening or starting right at the top of the ice shelf, we see the shallow. I don't think I have much time left, but for the key finding number 2, we see at higher frequencies, we see these different types of surface waves. So I showed this pulse of the Rayleigh wave of that high amplitude feature. Basically, the key point of this finding is that when we look in the frequency domain of these waves, synthetically, we can actually see that we can look at modal information as well. So the complete seismogram can be defined within looking at like different modes. So there's fundamental mode, first overtone, and we see that within the actual first overtone, so if we're looking at a wave on a string that's with no nodes whatsoever, we see there's a wave at the bottom of the ice shelf. And then if we're looking at the first overtone, that's where we see that Rayleigh wave. So that's where the Rayleigh wave is coming from. And that's kind of my thesis work in a nutshell. Thank you so much.
Excellent. Thank you so much, Dr. Bryant. We'd first like to field questions from the judges, and then we can open it up to our audience. So I will allow the judges, if you have a question, go ahead and unmute. So I see Dr. Hood's got his hand up.
Great presentation, Andrea. So I have a question about the instrument, the seismograph in particular. So I'm very familiar. So I'm very familiar with like a lot of the newer seismographs that actually get drilled down into the surfaces in order to measure like the P waves and S waves more efficiently. And that also helps like release some of the noise that you can get from your instrument. Since the Dragonfly, the JAXA, I believe it was called, since that's going to be sitting on the surface, how did you calibrate that to where things like the wind blowing in and possibly rocking it would be excluded from the measurements and included in noise?
That's a great question. So I'll caveat this with, I don't work on the hardware, but I do know that these noise is definitely going to be a big factor of the detection of the seismogram. So that we will get noise from winds. We'll also get some other noises just from the instrument, the actual the Dragonfly instrument itself. So we do know there are characterization studies of this, of the self noise and also wind noise and things like that. So we'll definitely have to subtract that out. But I think that work has been done also for similar work for like Mars Insight, where they also have a seismometer. So the Mars Insight, what do you call it? Seismometer mission was online for a couple of years and it just went offline. But they did similar things. So we just have to cancel out some of the wind noises. Like on Mars, you have like dust devils. I don't think we'll have dust devils on Titan, but we will have some other factors. But that's a great question. I think there's been a protocol that's been kind of perfected for Insight that can be, at least we'll have a start to know how to deal with those things. But I'm sure Titan will give its own particular issues that we have not seen before. But that's a great question. I hope I answered your question.
Hi, I have a question too. Excellent presentation. I've been kind of infatuated with Enceladus for several years now, and I think it's just really cool. So I think it's awesome that you get to work on Dragonfly and support that. I think earlier on, yeah, of course. Early on in your presentation, you mentioned kind of Cassini and how that kind of taught you all a lot of things about Saturn. And I was curious if you were kind of also borrowing lessons learned from the New Horizons mission, which maybe it didn't actually interact with the surface of Pluto, but it went out and it surveyed Pluto. And Pluto is actually very kind of similar to Enceladus in the fact that it's tidally locked with its moon Charon. It has cryovolcanism on the surface. It also has methane lakes and like reservoirs. So I guess my question is, have you all taken the chance to kind of look at similarities between that to see if you could steal lessons learned? And if not,
Oh.
how would you kind of go about doing that? Or do you think that there's an opportunity for there?
So for the with the New Horizons mission, I'm not. So I haven't. I'm not too familiar. I mean, I know of the mission, but I am not too familiar of some lessons learned that we've learned that particularly team members have learned. But I'm sure that we have. And honestly, there probably are members of the Dragonfly team who also were on New Horizons as well. I would say for my own particular work, since there's no planetary seismology aspect of that, I haven't looked at it in depth. But I would say that all of the things that we've learned, like as you said, similar methodology has been implemented for New Horizons and also for Cassini, and all the things that we've learned just with orbiter missions are useful for designing lander missions. So it's amazing what we can learn just by orbiting these planetary bodies and moons. So I hope that's to say I don't know much about the New Horizons mission, and I'm not a Pluto expert, but yeah, I definitely know that some of the methods that have been used for Pluto have definitely been used to learn a lot about Titan, which is amazing and helps us to design this mission. So maybe one day we'll have a lander mission to Pluto too. So because of New Horizons research.
Yeah, people don't care as much about Pluto, unfortunately. But I do think it's it's neat to see like similarities in the field and to see like, oh well, how did you look at this? And I'm sure you're also informed by the way that we study seismology on Earth too. So I think it's neat to kind of do cross contamination across persons.
Yeah, absolutely.
Excellent. We have a little bit of time. If there are any attendees that have any questions, I'm gonna go once. I'm gonna go twice. Okay, so moving on. Thank you so much, Andrea.
Thank you so much for having me.
Alrighty. So moving on to our next presenter, we will be hearing from Gianni Sims. A research overview of their work says that their research thesis focuses on understanding the seeding mechanism for supermassive black holes, SMBHs. Thus far, she has studied the active galactic nuclei, AGN, occupation, fraction in galaxies as a function of galaxy mass using data from the Deep Drilling Field Extended Chandra Deep Field South Survey, XMM-Newton Survey, and Elias S1 Survey. This work aims to distinguish between different SMBH seeding mechanisms by quantifying their distribution in these extensive extragalactic surveys. More specifically, they are fitting the spectral energy distribution of different AGNs to quantify the biases in identifying AGNs and better interpret the occupation fraction as a function of galaxy mass. Future steps in their thesis will include estimating the black hole mass using spectroscopy and scaling relations between SMBH and the host galaxy bulge mass. So without further ado, please feel free to start sharing and share your work with us.
Can you guys hear me? I just want to make sure.
Yes, we can hear you.
Okay, awesome. Let me just, okay. Right. Hi, everybody. My name is Gianni Sims. Currently a rising fourth-year PhD candidate at Florida Atlantic University. I currently work with Dr. Vicky Sarajadini, and this is part of my thesis as well. So I'm trying to understand how supermassive black holes were first formed by understanding their seeding mechanisms. So before I get to some of the work that I did, I just want to explain the arguments behind which seeding mechanism might be probable. So the first type of seeds is called light seeds. So this represents massive black holes that were formed from population 3 stars, or basically the first generation of stars during the early universe. And then the heavy seeds are formed from the direct collapse of gas clouds. And me and my advisor were reading a paper from Dr. Green, and we also read other papers that had different theoretical plots of distinguishing the different types of seeding mechanisms by trying to compute the fraction of galaxies that have supermassive black holes as a function of all galaxy masses. So in one of the theoretical plots that we looked at, an overall trend that we see is that the light seeds end up having a higher occupation fraction in general compared to the heavy seeds. There's a couple of things to note. So the light seeds have a lower threshold of how massive the galaxy can be in order for the supermassive black hole to form compared to the heavy seed model. Some models have it such that the light seeds might even be higher than what we looked at here in this specific plot here. That there may not be like a drop off for the light seeds in general, but there is going to be a drop off because there's a higher threshold of galaxy mass that's required for the supermassive black hole to form. So our main idea is that we wanted to use observations to replicate these theoretical models of the black hole occupation fraction. But before we did that, we wanted to try to select the galaxies that have an active galactic nuclei. So for AG, or another way of saying it is AGNs. So that's where there's a lot of activity and accretion in the surrounding environment of the galaxy. So we used observations by an academic paper by Dr. Zhou, and he selected approximately 2.8 million galaxies by using spectral energy distribution, so SEDs, and he used the large-scale structured telescope deep drilling field survey. So one of them is the wide Chandra deep field space, or they also call it the extended Chandra deep field space, the Elias S1, and the XM Newton surveys. So we wanted to try to select how many out of all these around 2.8 billion sources, how many of them have AGNs? So we used a statistical method from, again, Dr. Zhou, called the Bayesian Information Criterion method, or a short way of saying it is BIC. So each BIC method is supposed to create a more accurate selection method of choosing AGN candidates. So for example, for delta BIC 1, so this represents the first pass fitting returns of all of the galaxies. So out of all the galaxies, the delta BIC 1 chooses which one that might possibly have AGNs. Delta BIC 2 is doing the same process, but it's doing it from the raw SED AGN candidates. So the raw AGN candidates, that's from delta BIC 1, and then delta BIC 2 to have a more refined sources. They did the selection method from delta BIC 1. And then the reliable AGN, so that should be the most accurate method. That's again taking from delta BIC 2. So we used that method, and we wanted to compare those three different methods, and for all three surveys, and compare the different plots. So this is the plot we ended up getting. So there's a couple observations that we noted. So since reliable AGN has the most purity, or the most pure samples, which means it's the most accurate way of selecting the AGN candidates, we see that there is a more defined curve for the AGN fraction plot compared to the other delta BIC methods here. So the delta BIC 1 is not as defined, and then it slowly gets more defined as we go from delta BIC 1 to the reliable AGN. And that peak is approximately like 10 to the 10.5 solar masses. But one of the issues that we have is that there can be observational biases. We wanted to try to correct that AGN fraction. So far, we only wanted to do the correction for ECDFS so far. So I'm going to explain more about that, about how that was done. So what we did is that from not only Dr. Zhou, but also Dr. Luo and Dr. Guo, they wanted to choose a specific region of around 6 arc minutes in the ECDFS survey because they thought that this would have the deepest observation. So that means there might be more X-ray detection. So we basically created a completeness plot first from those X-ray sources. And based upon the specific region in the ECDFS survey. And then from there, we applied that completeness plot to correct, to overlap to our raw AGN occupation fraction. And this is what we end up getting as a result. So we see that overall trend is that the AGN, the occupation fraction, is a little bit higher than our raw AGN candidates plot, which makes sense because, again, the whole point is that we want to try to make sure that we have more completeness. We have more completeness than expected, which means that we want to try to find more AGN candidates that might not have been detected. But in the future, we are going to try to figure out different ways to correct the other ways to correct the AGN occupation fraction plot, mostly because in the beginning, when I made the completeness plot, some of the points when I averaged out, there were some empty spots here, so it's not the smoothest. So we're gonna go back to that. But what we see is that our observations so far coincide with the heavy seed modeling. We see that there's a drop off for the lower mass galaxies, and then that occupation fraction increases. So that kind of that matches well with the theoretical plot for the heavy seeds model. But there's still a lot more work to be done. So we want to, there's a couple things that we want to do. So far, we were trying to, we already completed at least one part of getting the AGN occupation fraction, but then the next step is getting the black hole occupation fraction. So we know there's activity in the center of the galaxy. You want to know for sure which of those galaxies have the supermassive black hole in the center. So we are aiming, that's going to be our next step. And another important thing is that another issue is that we want to concentrate more on the smaller mass galaxies. Usually they are the hardest to detect compared to the higher mass galaxies. So in the future, we might use Cosmos Web to try to have a more broad visualization of what that CD mechanism might look like. So the black hole occupation fraction that we have now might look a little bit different once we understand the behavior of the lower mass galaxies using Cosmos Web. And then our final thing is that to get the black hole occupation fraction, we need to get the black hole mass. So for the black hole mass, so far we've been using a linear relation, using Zhou et al. By comparing or having a linear relationship between the galaxy mass and the black hole mass, but we are skeptical of there being a linear relationship between the black hole mass and the galaxy mass. So we're gonna focus on trying to get the spectra of all the galaxies from all those galaxy sources from the SED fits, and then from there use a scaling relation or use virial theorem to try to estimate the black hole mass, and then from there we can try to get the black hole occupation fraction from there. So that's going to be our future plans, and that is it. Thank you.
Excellent. Thank you, Gianni. So again, we will field questions from judges first. And I do want to mention before we go on, attendees, if you have questions, please use the Q&A feature that Zoom provides.
Nice. Maybe I can go first this time.
Sure, Dr. B.
Yeah, excellent presentation. I learned a lot. I think black holes are super sick. Question is, I know that I have a lot of folks, a lot of friends who are in astrophysics, and their largest complaints are either there's way too much data or there's not enough data for us to make conclusions. So my question is, how did you and your team settle on the idea of only using 3 surveys to come to this, to come to your conclusions? And are you actually using like the full data suite available in those surveys, or are you taking a subset?
Yeah, that's a great question. So when me and my advisor were discussing, we both wanted to have we both wanted to choose surveys that have the most data. So I guess we're on the side of the argument of having more data. So that means there's like more probability possibilities. For now, we've been mostly focusing on the ECDFS survey to see, because not only it's much deeper compared to the XMM and the ALACE S1 survey, but it's so because it's so deep, it provides more uh, more possibilities of what the occupation fraction might look like, because there might be some galaxies, because there's going to be more data, there might be some galaxies that might not be detected as as having a supermassive black hole in the center. So we wanted to choose like surveys that have a lot more sources. But then in terms of like we also wanted to choose Cosmos Web, even though it's a little more there's not that many sources, but we thought that it would be better to really focus on the lower mass galaxies, because like the fields for all the possible galaxies, they're mostly gonna be showing more information of the larger mass galaxies. So that's why we wanted to kind of go back and forth. But for now, we're mostly using like larger like surveys that have like a lot more data, like ECDFS. So yeah.
I think that makes sense to me. So
Yeah.
thank you.
Yeah, no problem.
Great, Dr. Hood?
I feel like Dr. Payne like asked the majority of like the question that I also had, which was basically about the surveys and like why you chose to specifically use like the X-ray, like XMM Newton surveys that you did. But one thing that I can add to that is in that survey, XMM Newton and most X-ray surveys are, as my undergrad advisor says, astronomy is prejudiced to things that glow in the dark. So it only sees bright X-ray objects, similar to how Fermi only tracks really bright gamma ray objects. So there's an entire suite of AGN that you might be missing by only using the X-ray, and I believe the other survey was radio, I believe. So with the gaps in those wavelengths of surveys that you're missing, are you ever thinking about going back and using some in-between wavelengths to try to find sources that you might have missed? Because in my experience, it's like working with AGN, like the bright ones that you're seeing are typically either quasars and blazars, but there's also normal AGN that are bright AGN or semi-bright AGN that don't have like a lot of the same activity that you could be using to do some of these studies with.
So it's just it's kind of like, so you're asking if I'm planning on trying to find ways to detect AGNs of different wavelengths? Is that what you're asking, or?
Something like that. So like when you're only looking at like the bright ones, you are missing out on information from the dimmer ones that could more so complete what you're trying to do. So I was asking, like, are you thinking about doing that in the future as well, like to make sure that you have a plethora of different types of AGN that you can like use to like look at these black hole masses for?
Yes, and that's why we're planning on using, or partly why we're using the Cosmos Web survey to try to mostly focus on those smaller mass galaxies that might not have been detected, because right now it just looks like a total drop off just for the AGN fraction alone. But we think that there might be a lot of galaxies that are much dimmer that that aren't detected, but can still have AGNs or have a black hole in the center. So that's going to be more in the future, but yeah, we're planning on doing that.
Okay.
Yeah.
Thank you. That was it.
Okay.
Okay, we have two audience questions, actually. We'll try to get through those pretty quickly. So, Angela Meyer says, great presentation. What kinds of objects or phenomena could these AGN be hosting other than accreting SMBHs?
Kind of objects. So you back here. So yeah. So I'll just leave the question. Yeah. So I think if you have an AG in the center, we know that there can be a lot of activity in general at the center of the galaxy. If you have like there's still a high chance of it having a supermassive black hole in the center, which is why the AGNs will have a lot of accretion. That's why we are trying to detect these galaxies as having AGNs there too. So yeah, that's a good question. So there can be like for example, like near the center of the galaxy, there can be a lot of activities from different stars and other objects that might cause, or one of that cause might be a supermassive black hole. And I hope does that answer your question? I'm sure.
No worries. And you have another question from an anonymous attendee. I would like to ask Gianni, what does this work mean to them?
Well, so I guess this work means a lot to me personally, just because I've always wanted to work on black hole research. It took me a while to figure out what type of research I wanted to do. I kind of changed subfields, but I knew I wanted to work on black holes. And even my advisor, I spoke with my advisor. Her research mostly in the past had to do with like she works at AGNs, but she mostly worked on like the variability of galaxies that have AGNs. And I wanted to bring up to her about supermassive black holes. I think we had like a long discussion because at first I was like, oh, like maybe we can try to figure out how some of these supermassive black holes have gotten so massive. But then after some talking, my advisor brought up the paper of the different survey data. And she was like, oh, this is really good. Like these SED fits are really good. And there's a lot of data from the Chandra Deep Field survey, for example. So then we were like, okay, let's try and see how this goes from there. So yeah, so this work means a lot to me personally. Yeah.
Excellent. Well, thank you so much, Gianni. We will move on to our next presenter. Okay. And I think I may need to request that you stop sharing. Gianni, do you mind stopping your share? Oh, thank you very much. That's
Sorry about that.
no worries, no problem. Okay, moving on to our next presenter, we have Everett MacArthur from Stanford University. An overview of their research is they are searching for incredibly luminous accreting black holes called quasars that warp and distort background galaxies via gravitational lensing. It is their hope that using this geometric configuration that they can constrain the black hole to host mass scaling relationship across time. So thank you. Everett, please feel free to start sharing.
Yes. Okay. Sorry about that. Let me see. figure out my life real quick. Amazing. Okay. Can you all hear me? Awesome. Yes. All right. So hello, everyone. I'm Everett MacArthur, and I study highly luminous accreting supermassive black holes called quasars that warp and distort distant galaxies through an effect called gravitational lensing. Oh, let's hope this works. Okay. Yes. So the video that you're seeing is the visualization of this effect, where a foreground collection of galaxies viewed from a telescope have a galaxy in the background. And so if you look through this configuration, you can see that the galaxy, which you are seeing now, that's the background galaxy farther away. And the two foreground galaxies are going to lens that background galaxy. And so through this lensing effect, we can precisely understand how we can characterize the mass of the host galaxy, essentially. And so J0919 is a very interesting case where you have a quasar and the host galaxy that are acting as lenses for that background galaxy. And so the way you can think about this is like a glass cup in a kitchen cabinet, where by holding that glass cup in front of a distant object, you'll see those distant objects being warped and distorted around that glass cup. And so like that glass cup, you have a foreground quasar and the distant object being a background galaxy, essentially. So by the end of this talk, it is my hope to deputize all of you, essentially, to help me in the search of quasars acting as strong lenses, because this is an incredibly rare configuration, but very revealing to how one can precisely weigh a galaxy, essentially. And so as of right now, 3 of these are known, and they were confirmed through HST imaging, so Hubble Space Telescope imaging. What you just saw in the previous slide was J0919, where 2 galaxies, the quasar and a foreground galaxy next to it, lens the background galaxy, and the arrow is pointing towards the lensing configuration, or the arc of that background galaxy, essentially. And so in Mion et al. 2023, they were able to use that lensing configuration to precisely measure the galaxy that hosts the quasar. Now, to a note on the geometry here, you have the quasar and you have the host galaxy. The host galaxy is what we want to measure. The host galaxy is the mass that we want, because to measure that mass, it is difficult. Quasar luminosity makes everything bright, and so to use photometry to measure it, you have a massive error. And the orange point essentially shows how the error around that using photometry is quite large in comparison to the blue point, which is using lensing. And so using lensing, they're able to precisely measure that host mass by using that quasar that acts as a strong lens. And so just a note, the y-axis is the black hole mass and the x-axis is a host mass. The x-axis being the horizontal and y-axis being vertical. And so the host mass is what we are interested in. And that blue point is the thing that we are looking for. We want to constrain the error bar around all of the quasars for their host galaxy using quasars acting as strong lenses. And so we want to increase this short list. 12 strong candidates were identified in previous literature, and these strong candidates were found spectroscopically. And so they essentially looked to find signatures of a more distant galaxy and the foreground galaxy's emission lines or features in the spectrum to identify whether or not it is lensing something. And so with millions of quasars in the dark energy spectroscopic instrument, it is our hope that we can dramatically increase this short list of candidates, essentially. And for those of you who don't know, the Dark Energy Spectroscopic Instrument, or DESI, sends astronomers, astrophysicists, high resolution spectroscopic measurements of millions of objects. So this presents a unique opportunity to truly study this configuration and really make use of spectra to identify these quasars. But we want to do this using machine learning, because using machine learning, we avoid the tedious looking at spectra one by one and hoping that there's something in there. If there's millions of spectra, it's almost improbable to ask one person to look for one quasar individually throughout millions or 70 million quasars, essentially. So machine learning is scalable, and it will allow us to develop a sample of quasars that can truly tell us something about how galaxies evolve across time, essentially. So ideally, it is what we are looking to do is to design an algorithm that will essentially look for two things: features from the higher redshift background galaxy, essentially, and features from the foreground quasar. Now, what I'm showing in this plot is flux versus wavelength. Flux being intensity and wavelength being wavelength, essentially. And so the black line is a total spectrum. That is what we expect to obtain from DESI. And then the red line is the background galaxy, and the green line is the quasar itself. And what we expect to find in DESI is the black line, the superposition of the red line and the green line, where the black line is dominated by the quasar, essentially. So what I'm showing right now is a lower redshift emission, essentially. And then at that same redshift, I'm also indicating an emission from the quasar as well, which is broadened. So quasar emissions are always broadened for the most part as a result of material orbiting around the black hole. Now, if it is lensed, then what we expect to find is emission from that background object as well. So we would identify features from both the background and the foreground galaxy using machine learning, essentially. So on that note, we were able to design a machine learning algorithm, and we were able to identify at least 100 candidates, which is phenomenal. And we want to develop a statistical sample of strong lenses to enable black hole mass to host mass relationships across time, across redshift. And using this 100 sample, it's really a starting point. And so if you are interested in reading more about this, I did link the QR code to a blog post that I wrote some time ago. And I want to thank you all of you for listening. And on that note, if there's any questions, please let me know.
Dr. Fields, please feel free to ask your question.
Awesome. Thank you for that great talk. I just had a quick question. So you mentioned using machine learning, and I wanted to very briefly unpack that. I was just curious, is there an algorithm or I guess method that y'all are leaning on where sort of the process was really just identifying features that would be most helpful in those spectra to go, to be flagged as part of that algorithm, or do you guys utilize something novel within the machine learning framework?
Yes. Yes. So I did skirt around that because I know there's a can of worms, and I expect to get a lot of questions on machine learning side. But to answer your question directly, we are using what's called a convolutional neural network. So a CNN essentially has convolutional layers that filters out all of the noise, all of the stuff that we don't really need in the spectra. And what the end result is, it'll output either a lens or not a lens, basically. It's a classifying CNN. So you have convolutional layers and you have a fully connected layer. The fully connected layer is where the decision making is happening. The convolutional layer is where it's filtering everything out and basically obtaining a convolved spectrum that has all of the features that the neural network will identify and use those features as a way to identify lens or not a lens.
Awesome. Thank you. That was a great explanation. That's exactly what I was looking to hear. Thanks.
Okay, I think I saw Dr. Hood first, and then we can go to Dr. Payne.
Oh, it was Dr. Payne first. Sorry.
I'm sorry.
Oh, it's all right. I'll go ahead. So my question was, you mentioned that most of these sources have broad line emission. That's specifically for quasars, correct? Is that what you were referring to?
Yes.
So in the cases where there are narrow line emissions, what does that tell you about the system that you're looking at? Or have you ever come across situations where you have both broad and narrow line emissions within a period of observations?
Oh yeah, of course, definitely. So the majority of our sources, when I say broad line, I mean that broad lines are a result of material closer in towards a black hole that is incredibly moving fast, essentially. So you have this narrow line that's being broadened essentially as a result of them moving really fast. Now, quasars also have, this is called the broad line region, by the way. Quasars also have a narrow line region, which is basically either material from farther out from the black hole, and that narrow line is basically from the host galaxy, essentially. And so it is possible that you can obtain both of those, the broad line and the narrow line, in the full spectrum. And to be honest with you, I wasn't aware that there was something called the narrow line region. So when one of the candidates popped out saying, we have all of these narrow lines, I was like, we have one. We have a quasar acting as a strong lens. And then, I was basically, my bubble was deflated. So long story short, there are many quasars that do have narrow lines as well as broad lines. In our sample that we use to train the neural network, there are many of them that possess that. And so the network um, isn't going to weight that heavily as a way to identify a lens or not a lens. But it isn't out of the question that you would have one identified as a candidate, because really, broadly speaking, ignoring feature emissions and ignoring higher redshift and lower redshift, when you have a quasar acting as a strong lens, what you have is a higher distribution of emission lines, essentially, because you have emission lines from the quasar and you have emission lines from the background galaxy. And so if you have a quasar that has all of these broad lines and all of these narrow lines, then it's no question that the neural network is going to pick it up, because you have all these emissions all over the place, essentially. That was a very long explanation to your question, but
It's good because you answered the question I was probably going to email you as a follow-up too. So thank you.
Amazing. Good job. Great presentation. I obligatory James Webb question because it's necessary. Because the universe is vast and chaotic, I can imagine an instance where you would have a quasar that is kind of co-aligned with maybe perhaps two galaxies in front of your observation point. If you were to get a target that had multiple emission types for multiple galaxies, would your machine learning algorithm be able to differentiate between the two kind of lensed targets in front of you? Kind of part one. Part two, is James Webb at all useful for your work in the types of in terms of the type of data that it's getting for these types of targets?
I'll answer part two as yes, it is going to be useful, but unfortunately, it's very oversubscribed. So they're just using a Hubble telescope to identify everything. That's just easier, or at least I think it's easier. I don't know, but ideally we'd follow up these objects with HST imaging. Now, to your first question, and I saved that one for last because it's a little bit more involved, but long story short, no, it isn't necessarily able to identify those sorts of objects. So when I say 100 candidates, what I really mean is we have 100 candidates, but another 100 are identified as candidates as well. And
Okay.
that is understandable because many of these objects, so going back to my explanation about having this massive distribution of emission lines, if you have, a note on DESI has a fiber essentially, and the fiber is 1.5 arc seconds in diameter. And so when it identifies when it takes a spectrum of an object, then that fiber is small, sure, but if you have a foreground galaxy right next to the quasar, like say the quasar is right here and you have this massive galaxy right next to it, then you're going to catch the flux of both those galaxies together, essentially. And so the spectrum is going to look like you have something being lensed, but really it's not. And really it's just you have those two galaxies next to it. So if in the off chance that we do have like these two galaxies superimposed over each other, and then in the background we have this lens, then it is possible that you'd have something like that. But I would be disinclined to really say that it's a strong candidate because you have all of these emission lines, and it would require some really hand wavy stuff to really justify it being a lens, essentially. But yeah.
Nice. Sweet, thank you.
Wonderful. So you've also got some attendee questions. And if at any point we don't get to your questions as an attendee, the panelists can write back to you through the Q&A feature. So just keep that in mind and feel free to continue asking questions.
I didn't know about
so the
this,
first,
guys.
yes, no, yeah. Even if you've already presented, please feel free to answer questions through that feature. So Floor Broick Garden says, really stellar talk. Could there be any binary lenses from binary quasars?
Oh yeah, for sure. And for a decent amount of time, we were actually convinced that we had like two quasars acting as the lens. Granted, it's rare. I will say it is very rare, and I think definitely do not quote me on this. Well, it's recorded, so I guess quote me, but don't take don't take it don't take it face value, as I believe there's probably 2, 3, or 4 that there are definitely quasar lenses. But it's not what we're looking for, and they're definitely not frequent. But the reason why we thought that we had a quasar lens was because in one of our candidates we had emissions that didn't match to anything. And we were like, oh, well, it looks like those emissions are pretty broad too, so it looks like it can be a quasar. Long story short, it was not a quasar lens. Yeah, but it is possible. Is it frequent? No. Is it going to be a diamond find? Yeah, for sure.
Okay, thank you. An anonymous attendee says, thanks for an interesting talk. Are you going to use Zooniverse or any other classification method that can also support the developed machine learning pipeline, kind of like verifying the result?
I am not familiar with Zooniverse, to be completely honest with you. I've heard about it, but I'm not an expert on it. But I think to pick apart the question and ask about like verifying results from machine learning algorithms. So in a perfect world, we would identify strong candidates using that classification. And then from there, so here's a subtle thing I did not say at all. And in fact, I didn't even address it, was that the classifier is going to identify a lens or not a lens. That's great. But if we want to say that we have something in the background, we need a convincing redshift or a redshift solution of that background galaxy, essentially. So we have the redshift of the quasar, which means that it's fairly close to us. So like, let's say 0.9 redshift means it's very close. If you have that quasar identified as a lens, then that's great. We know that the quasar is at 0.9. That's fantastic. But if it's a lens, then how far away is the other galaxy? What's the redshift of the other galaxy? And so to say that these are strong candidates means that we have both a redshift solution for the background galaxy and it was identified as a lens. So really there's two neural networks going on here, which I didn't say anything about. But the first neural network is the CNN, which is a classifier. And then the second neural network is a redshift finder. So we feed all the spectra into the CNN that gives us a lens, not a lens. Then we feed those spectra into the redshift finder, and then it will find a redshift for that object, essentially. Then we can verify it by using DESI's spectral viewer to see, okay, is that redshift solution correct? And then from there, we can say, okay, now we have a really, really strong candidate. That's great. And then in a perfect world, we would verify all of these objects using HST imaging.
Excellent. And your final attendee question is from Octavia Nettles, who says, great presentation, Everett. Thinking back, what were you most excited about when you were making this presentation?
Um, um, uh, I guess that's a tough question. That is a very good question. I would say probably just telling you all about this, in all honesty. Um, I think my goal when creating this presentation was that I wanted to tell you all about a cool thing in science. That is it. And I wanted to make sure that all of you will walk away saying like, wow, those quasars are lensing something out there. And whether or not you study quasars is completely irrelevant. But if you walk away with just saying, wow, that's really cool, then I'm happy. And I hope you're happy and I hope you're not bored.
Great answer. Thank you for your presentation. We're going to go ahead and move on to our next presenter. So I will begin sharing again. So moving on to Victor Oyiboka from the University of Texas at Dallas, whose research interview states the YMIR mission, Enceladus Biosignatures Detection Mission. Here they propose to use instruments such as Raman spectroscopy, e-THEMIS, UV fluorescence spectroscopy, and light field volume fluorescent imager to determine if hydrothermal vents on Enceladus have chemicals that can help life grow and develop like those on Earth. Their mission goal is landing on the south pole of Enceladus, studying the composition and location of plumes, looking for biosignatures and comparing them to sulfurimonous pluma. Please forgive me. The mission architecture is a 4-leaf clover rover design with each leaf detachable from the base. The leaves are connected to the base via tethers. So please, Victor, whenever you are ready, please start sharing.
Yeah, can you hear me? Hi.
Hi,
Yeah,
and
can
we
you
can
hear me?
definitely hear you.
Okay.
Yes, we can hear you. Mhm.
Yes. Yeah, let me share my screen. Oh, yes. Yeah, can you see my screen?
Yes, we can.
Yeah. So the Yama mission. So our mission goal, first of all, is to land on the south pole of Enceladus. Also, we are to study the composition of the plumes. We'll also look for the biosignatures similar to the sulfurimonous pluma. And lastly, we'll look for characteristic chemicals of hydrothermal vents. That's our mission goal for the Yama mission. Secondly, the scientific purpose of this mission is to check the surface and the plume composition on Enceladus. So Enceladus is the 6th largest moon of Saturn and also the 19th largest moon of the solar system. So we are looking for the surface and plume composition on Enceladus. We are also finding if plumes have chemicals that can help life grow and develop like on Earth. Thirdly, we'll confirm the presence of hydrothermal vents through characteristic chemicals of hydrothermal vents, because this is a future mission. So we are also looking at this. Then the instruments we are going to use are the Raman spectroscopy with NIR laser, the e-THEMIS, which is a thermal imager, the UV-Vis fluorescent imaging spectrometer, and also the fluorescence light field microscopy. This is about the mission architecture. So we have the four instruments we are going to use: the Raman spectroscopy, the light field volume, the fluorescence, and also the e-THEMIS and the UV fluorescence spectroscopy. The mission architecture is a 4-leaf clover design with each leaf detachable from the base. So also the leaves connected to base via tethers is detachable if causing problems with physical barriers and sensor feedbacks. The communication which we're going to be using are the high gain antennas, and also the power source, which is the radioisotope thermoelectric generator, is a power source. Lastly, the sample mechanism is a specialized sampling collector for falling debris from plumes. We're going to be highlighting the uses of this instrument. For instance, the Raman spectrometer with the NIR laser will be used for the analysis of the chemical composition of the plumes, which will be useful for detection of biosignatures. No sample preparation is required, and also it's portable and non-invasive. For the e-thermis, which is a thermal imager, it will be useful for the analysis of chemical composition of plumes and surface. It's also non-invasive and no sample preparation is required. It will also be used for checking minerals and biosignatures. For the UV fluorescent imaging spectrometer, it will be useful for the surface imaging of the crust, detection of areas of surface where the ocean can be closer for future crust drilling. Lastly, the fluorescence light field microscopy will be useful for the detection of biosignatures specialized in bacterial composition. In academic papers, the spacecraft design is often considered secondary to the scientific instruments and goals, but it is an interdisciplinary endeavor that involves aerospace engineering. So I did this especially because I know Black In Astro, we have mechanical engineers, we have aerospace engineers, we have people from the computer science field, different fields. So I took cognizance of the spacecraft design. The spacecraft will largely depend on the mission objectives, the payload requirements, and technical limitations. Here are some considerations. So we'll consider some things from the aerospace engineers or also from the mechanical engineers. So the payload will need the instruments for Raman and IAC spectroscopy, which may require cooling systems. For the sampling mechanism, we use to study the hydrothermal vent, which is a specialized sampling arm or probe which might be necessary. The power source, given the distance from the sun, we may need to consider a radioisotope thermoelectric generator, like the one used for the Mars Curiosity rover. For the communication, we need high gain antennas, which will be essential for transmitting data back to the Earth. For the propulsion, a propulsion system for orbital adjustment and potential landing or hovering capabilities. And the thermal control, Enceladus is far from the sun, so thermal control systems will be crucial for maintaining a stable environment for the instrument. Also for the automation, due to the long communication lag with Earth, autonomous operation capabilities will be vital. For the shielding, we will also need to shield it. The spacecraft may require shielding against radiation, given Saturn's magnetic environment. We will need to shield it with a polyethylene. The concept of a four-leaf clover like rover with detachable leaves is an innovative approach to rover design. The idea seems to revolve around having separate modules that can move independently while being connected to a central base via tether. So also, there are also risk of tangles. Yes, there's an inherent risk of the tethers becoming tangled if the leaves move independently without coordinated control. So if the four leaves are moving independently without the control, there will be a tangle. If also the terrain is uneven, leading to unpredictable movement, the tethers aren't properly managed or retracted, it can also cause tangle. To prevent tangle, here are some suggestions. There needs to be a coordinated movement. The movements of all leaves should be coordinated in a way that they don't interfere with one another. This would likely require sophisticated algorithms and sensing capabilities. Also, there needs to be an active theta management. We need to incorporate mechanisms to actively manage theta slack. For example, motorized reels can be used to extract or release the thetas as needed. For the sensors feedback, we need to implement sensors on the thetas or the rover module to detect tension or potential entanglement. The system can then make adjustments to avoid tangle or stop movement if a potential tangle is detected. So the engineers need to take note of that in case of tangle. And also for the physical barriers, we should consider placing barriers or guides at the point where the theta's connect to the central base, ensuring that they have separate paths and reducing the chances of overlap. Also, for redundant systems, even with the precautions, there's always a risk of tangling. It might be helpful to design the system so that if a theta becomes problematic, it can be detached easily or isolated without compromising the entire mission. We also need to simulate and test this clover. So before deploying such a system, it would be crucial to run simulations and physical tests in environments that mimic the intended deployment site. This will allow us to anticipate and address potential issues. For the theta material and design, the choice of theta material and its design, like the flat versus round, textured versus smooth, can influence the likelihood of tangles. Some materials or designs might be less prone to tangling than others. And we also need to take cognizance of the terrain awareness. The rover should be equipped with terrain mapping and awareness capabilities. If it can anticipate and navigate around obstacles, it can reduce the chances of thetas getting caught or tangled. So incorporating some of these strategies should help in reducing the risk associated with a theta multimodal rover system, although it's a challenging problem, but not insurmountable with careful design and engineering. So lastly, we'll also be looking at the chemicals in hydrothermal vents. Hydrothermal vents on Earth are rich in minerals and chemicals like sulfides, methane, hydrogen, and various metals. Just why the exact composition of Enceladus hydrothermal vents is not known, the Cassini spacecraft detected organic molecules, molecular hydrogen, and other life-supporting compounds in the moon's water plumes. So I know you have been asking me what's the meaning of Yama mission, YMRI mission. So the name Yama comes from Norse mythology. Yama was a giant the first being created from ice and heat. Just like YMIR, our mission revolves around the identification of life on Enceladus, which is Saturn's moon. And also, we look at organisms that thrive on ice and heat, like the environment of the icy giant. So that's my presentation for today. Thank you very much.
Thank you so much, Victor. As usual, I'll start with questions from our judges.
Yeah, I can go. Yeah, thanks so much, Victor. That was really interesting. I guess my question for you is, given the challenges of observing something like Enceladus, where the environment is really extreme, in terms of getting the spacecraft there and then also looking at Enceladus, which is inherently, an extreme environment kind of wrapped into a moon. And outside of your spacecraft risks that you talked about, like getting tethered or getting tangled in your own tethers, what do you think is the most challenging aspect of the spacecraft design, for, observing something that extreme?
So I would say the most challenging aspect of the spacecraft design will be the engineering part. So like getting the thetas to work and getting everything to work to land successfully on the south pole of Enceladus. That would be the most challenging part. The rover design, so it will really be a challenging part. That's the most challenging part. So on a norm, this is supposed to be like just a science paper, but I saw that we have different fields in Black In Astro. We have aerospace engineers, mechanical engineers, computer science, computer engineering. So I took cognizance of those challenges. So the engineering part it's a huge challenge. The engineering part is a huge challenge in this mission.
Yeah, getting all the parts to play together is always really hard. So yeah.
Yes.
Yeah, thank you.
Thank you.
So I know it's not an exact one-to-one kind of like testing environment, but have y'all considered doing something like taking like a test payload to like McMurdo Station in Antarctica or Greenland, to one of those like experimental bases out there to do a test like launch, landing, see how the equipment handles like cold weather and things like that?
Okay, okay. Sorry, I didn't get your question. Can you come again?
Sorry, I couldn't hear you.
I didn't get your question. Can you please come again?
Oh, I was asking, have y'all considered taking your payload once you get it operational to somewhere like McMurdo Station in Antarctica or to one of the research bases in Greenland to test it out in cold weather and see how it maintains itself here?
Oh, no, we have not done that. So we are also looking forward to that because we are just four researchers from different countries and different continents of the world. So we came together and proposed this mission, and we are looking forward to make it happen, like make it a reality in the future. So we are just putting things together in place and trying to work it out. Yeah, so this is just the beginning stage. This is the background. So,
Okay, thank you.
yeah, we'll consider that. Thank you very much for that. We'll consider that. Thank you. I really appreciate it.
No problem.
Wonderful. That's the purpose of these research showcases. You get some really good ideas. So moving on to attendee questions. Anonymous attendee again says, hello, Victor. Bravo. What does being in this showcase mean for the communities that you serve?
Sorry, what can you come again? I didn't hear clearly.
Sure, absolutely. They said, what does being in this showcase mean for the communities that you serve?
Oh, wow. That's an interesting question. I would say being in this showcase, it's a huge opportunity for me. Like I I've been I've been longing for this. I joined the Black In Astro, right, like about 2 years ago, and from there I applied to grad school. I'm an incoming PhD student at the University of Texas at Dallas, so I will start my first year this fall. So being in this showcase is it's a huge one for me, and it's to open me. I'm sure it's open to. I'll be open to more opportunities in the future, more collaborations, more research, and I can't wait to see you all right in the US very soon. It's a huge one for me. Thank you very much.
Of course, and we're so happy to have you. And I actually have a question of my own. I did notice you
Yeah.
mentioned that you'll need some propulsion for orbit maintenance. And I was curious if you've done any trade studies on what propulsion systems or types you would employ for that.
No, I've not done that. I've not done that, but it's also in the pipeline. It's also in the
Well,
pipeline,
please
so
stay
we'll
in
look forward to
touch.
that.
I'm an
So,
electric propulsion advocate. But
yeah.
great
Oh,
job.
wow.
Thank you for your presentation.
Thank you. Yeah, thank you very much. Have a nice day. Thank you all.
Of course. So now moving on to the next presenter. Give me a minute to get it pulled up. So we've got Miles Pope from Johns Hopkins University, and their research overview states, they report on the new star and XMM-Newton observations of the high mass gamma ray binary IFGL J1018.6-5856. They find that with the extended observation period to include the 2023 pre-periastron spike and well into the peak of the spike, the spectral shape hardens with increasing flux, which is consistent with previous measurements in An et al. 2015. In the near future, they plan to cross-correlate the X-ray light curves with Fermi LAT data and ATCA radial data to extend their knowledge of the binary. This is a project that they have worked on in their senior year at Howard University and are continuing this summer at NASA Goddard Space Flight Center. So Miles, please share when you are ready.
Okay. And this is leave. Now I'm sharing. Yep. So can everybody see the presentation? If it loads, there we go. Should be able to see it.
Yeah.
Okay. So
Yes, we can see.
okay, start now. So good afternoon, everyone. My name is Miles Pope, and I recently graduated from Howard University, and I'm going to be an incoming first-year PhD student at Johns Hopkins University. And this is a project that I worked on in my senior year, and I'm currently working on this too at NASA Goddard Space Flight Center with my mentor, Joe Coley, and another grad student at Howard, Courtney McIntosh. And what we were focusing on this project was an X-ray analysis of the high mass gamma ray binary 1FGL J1018.65856. So that's a really long name. So from this point on in this presentation, whenever I'm going to be referring to the source, I'm just going to be referring to it as J1018. To give a little bit of scientific background about what's happening in the source and why we're interested in it is that this source is a high mass gamma ray binary. And what a high mass gamma ray binary is it's a system where you have a star. Usually it's a massive type star that's an early stage one. And you have a compact object that's a companion of it. Now, the compact object, it's some sort of stellar remnant, so it could be a black hole or it could be a neutron star. And those two, since they're close to each other and they're similar size and mass, they're going to orbit at one another. And you're going to see the gravitational orbit between them, and that's going to create the binary. And what we were looking at in this project was studying the interbinary shock from them, which the star is going to have some wind that's associated with it from a whole bunch of particles that it's ejecting. And that wind's going to interact with whatever's happening in the compact object. And the wind from the star, that's mainly going to be in the UV range, since this is mainly stellar radiation. But for this source, we see a lot of stuff in X-rays and gamma rays. So that means that there's something happening between the interaction between the stellar wind and the compact object that's really accelerating these photons to much higher energy levels. So that's what we were trying to probe with this project, to see what the mechanism behind this particle acceleration could be. And this diagram right here is just showing off what the system looks like. And this right here, this little light blue section is really the area of interest that we were mainly looking at, because we found that at this point in the orbit, there was a big spike in the flux between the radio, the X-ray, and the gamma ray. There's a really big spike in the flux. So we knew that there was something happening here that was showing across all the wavelengths, and we were trying to figure out what was happening there. So the methods that we used for this project focused on a 2023 observation from NuStar of J1018. And basically the TLDR of how, when you're doing astronomy, how you're doing observations and things like this is you start off with whatever telescope you're using, and you need to find a certain time that you're going to do it for. So this right here is just an image from Swift, which is also another telescope that we use for this observation. And this is just basically showing what the source is looking like. And once you hone in on kind of this region right here where you have the source, you can find the amount of photons that you're getting from the source, and then you can find the amount of photons you're getting somewhere from the background. And from that, we can produce two types of products. We can produce light curves, which is telling us the count of the photons over their time that they're happening. And we can produce spectra, which is telling us the count of photons versus the energy. And with that, there's a lot of information that we can find out about the source. So for this analysis, it was done mainly using a mix of Python packages and a lot of tools in NASA's HEOSOC software, which is basically the country's high energy astrophysics archive that has a lot of information and a lot of software for doing high energy astroanalysis. And for me personally, I didn't have this installed on my computer because it's a lot of work, and it takes up a lot of space to download all these packages. But luckily, there was an online interface, SciServer, which already has Python installed and HEOSOC. So by using SciServer instead, I was able to do all of the analysis on that instead of having to do it locally on my computer. And this right here is just the light curve of our observation that we got from 2023, which you can see that this right here is the spike that I was talking about previously, because you have a rise in flux and then you kind of have a peak in flux and then it starts to decay a little bit. And this right here is the main thing that we were focused on for this project. So once we were able to find a light curve, we phase bend it, which is just taking the light curve and telling what part of the orbital phase it's happening in. And then once we did that, we were able to do some phase resolve spectroscopy of it. And for this, we use archival data from XMM Newton and our new data for New Star to see what the spectral was looking like and how the counts were changing based on the energy of the photons that we were seeing. So once we looked at the spectra, we decided that the best model to fit it would be an absorbed power law model, which would give us a photon index, and it would also give us the flux of it. And the reason that we had to do an absorbed power law was because between us, the observers on Earth, and the source all the way out there in space, there's a lot of things in between them, which is mainly the ISM, the interstellar medium. So we had to do it with an absorbed power law to account for all the absorption from the source between us from the ISM. And once we were able to do that, we were able to do some time-resolved spectral analysis on it. And we split the new star light curve that we had from this newest observation into four equally spaced bins. And what we found some very important things once we did this. We found that there was no evidence of a high energy spectral cutoff or spectral break with the time-resolved spectral analysis. And that's basically telling us that, okay, we're looking at this and we're not seeing the evidence of what we would expect if we were having a source that had a compact object that was having some sort of accretion mechanism happening. So we're not really finding evidence on that, which is leading us to believe that, like some previous systems, some previous high mass gamma ray binaries where we actually know the compact object, this one, it's probable that it has a neutron star pulsar that's accompanying it. But we can't say that for certain yet. So don't 100% quote me on that. But right now, from the spectral analysis that we got from New Star, that's what it's looking like. And we also found that as the spectral shape hardens as the observation goes more deeper into the peak. So as the flux increases, the spectral shape is hardening. So that was also something that was really impactful that we were finding. And this is just the X-ray result that I've done so far. But what I'm working on right now is I'm looking at Swift data, and I'm basically reproducing some of the results that was done in Han et al. 2015. So this chart right here will be populated more so here with a lot of Swift data, so we can constrain better what this best fit line will look like for the spectral, for the photon index and the X-ray flux. And additionally, on top of that, we're going to start doing a pulsation search in the X-ray so that we can find out if we're seeing pulsations in the X-ray, so we can kind of determine, is there a pulsar here or not? Now, we don't expect to really find it just because there's not a lot of data on this, so it's kind of hard to find pulsations when you don't have that much data. But those are the next two steps for the X-ray part of this project. But this is a multi-wavelength analysis at the end of the day. So there's also a lot of work that I'm not personally working on, but some of the collaborators on this project are also working on some of the things that are happening within the gamma ray and within the radio data. So I think that, especially the gamma ray, I'm really excited to see the results that come out of that. So the conclusion and acknowledgement to this presentation is that our analysis revealed that as the system goes deeper into the spike, the photon index hardens. And I would also like to give acknowledgement to all of these sources that I cited for the telescopes that we use for Swift, XMM, Newton, and New Star, and also the grant that we got to actually observe this source last year. And also to some other collaborators who have done a lot of the groundwork on this project before. So On and Van Soellen, I'd like to also give them a shout out. And finally, give a shout out to Howard University and NASA Goddard Space Flight Center for hosting all of us who have been working on this project. And now I will take any questions. And look at the Q&A. Okay. So I don't know who raised.
Yeah.
Okay, Dr. Payne, yes.
I'm sorry, I was saying, I think Dr. Hood was first.
You can go first.
Okay. Excellent talk, Miles. This is great. Also congratulations on starting grad school. To you and to Victor. I forgot to congratulate Victor as well, but that's very exciting. I'm curious. So you mentioned that one of your results so far, which I know you said you have more work to do because it's multispectral, and so far you're only looking at X-ray. But so far, one of the results is giving you things that you didn't expect to see. And I was curious to know if you all were going to run the same type of analysis, but with a different tool to see if the unexpected results are present there too. Because in doing so, then you could definitely be like, okay, this thing is from a source that we like that is unexpected, and it's not just bias from the type of tool that we used.
Hmm. So
Mhm.
when you say a type of tool, are you talking about like a programming tool or a different type of instrument that we will be using?
A different type of tool, but I guess similarly, you mentioned that you were using Swift data, but there's also Chandra X-ray data that I used when I was an undergrad, and it was really useful. So I guess maybe are you planning to use that too, or?
Yeah, so that's Chandra. That's definitely something that I think could be helpful. I would have to ask my mentor a little bit more about that, whether or not
Sure.
Chandra data will be useful, because I'm not exactly sure the energy range, but I know one of the reasons, and when we wrote the proposal to get the observation, one of the main things was that we needed to look at harder X-rays because we already had a lot of Swift and XMM data, but it wasn't
Mhm.
exactly, we wanted to also look at the hard X-ray spectrum as well, which is mainly what this paper focused on, because we were really looking at like 3 to 25 keV. Since above 25 keV, that's when we really got a lot of background domination. But yeah, it's definitely something that we could look at.
Sure. Yeah, and then yeah, I guess my first question was regarding the tool. I don't remember what tool you used. You said the name of it, but if there's another option to use some similar kind of open source Python package,
Oh,
to run your data through that too and be like, oh yes, we're definitely seeing this result here and in this tool, then you can like you have a conclusive study of like, oh, this thing is real, like the effects that are unexpected are actually happening in our data, which would be really cool, I think. So yeah.
so the tool that we were using to the tool, there's actually a few tools. So the one that we were using to fit the spectra, that's XSpec, which is part of NASA's HEOSOC software,
Right, right.
is one of which is like the main one. That's kind of like the standard one that's used for like X-ray analysis. Mainly people use that for like fitting, doing a lot of stuff with X-ray spectra. But there is also this tool NAIMA, which is also another one that we can look at, and also Stingray. Stingray I actually did look at, but I wasn't able to. Still needed more time to completely figure out how it worked. But that was a Python package, and also Naima. That's another package that can be used for X-ray analysis. So that's definitely something that we've been thinking about doing.
Yeah, it might be interesting to compare, you know.
Mm.
Yeah, thank you. Great talk.
Now for the next question, Dr. Hood.
Yeah, so um great talk. Also, congrats to you and Vicky, because I also forgot to mention that I'm starting grad school. So in the beginning, when you showed your diagram of the binary system, there was like the blue region where you said that there was like a extreme bright event that happened across all wavelengths.
Yeah.
Have you investigated that to see if that was some sort of like synchrotron dominated like flaring event that happened, or what are the possibilities of things that could have been going on then?
Hmm. So when we were originally doing this, we were looking at Swift data, and that's where we saw this big peak, where we had this big spike in flux right here that happened right before periastron. So that's why when we went to New Star, we started to observe at that point specifically to figure out more so what's happening there. And from the spectra that we got, it looks like that it's synchrotron happening there. And this is something that's kind of continuing into the gamma ray. This is also continuing there because it looks like we have synchrotron that's definitely happening in the X-ray. But it looks like that as we go into the gamma ray, we're also starting to see some inverse Compton. So that's stuff
Mhm.
that's been like floating around too. So that was like mainly the two types of radiation or the two types of acceleration that we were looking for, synchrotron and inverse Compton. And since this is also synchrotron, that also, it looks like it's synchrotron from the spectra, that also kind of leads towards the idea that this is a pulsar that we're looking at. as the compact object, because then you have the magnetic field that's accelerating the
Okay. Are there any types of follow-ups or additional observations or data that you can look at to more so narrow down what it was?
So that was the point of this project. This project was a follow-up, so we're still doing that. We're also looking at, in the game array, we have a lot of data for game array. We have a lot of Fermi data for it. We don't have that much X-ray data though. This is the first new star observation of the source, and this is we actually have a decent amount of XMM Newton data. So here you can see the XMM Newton data where we're seeing something similar happening, where we're also seeing similarly that it looks like it's a power law that's happening. And you can also see right here, we have these two blue points that are plotted right here, which is showing the XMM data that we looked at.
Okay, thank you.
Great job, Miles. Do the attendees have any questions? Okay. Well, this was our last presenter. Thank you so much to all of our presenters. Your work is super fascinating and you are all extremely brilliant. Thank you to our judges for lending your time and expertise. Thank you to our attendees. I hope that you learned as much as I did. We do have a few more minutes left in the session if there are any more questions for any previous presenters. If not, feel free to connect with them after the panel. Okay, we do have an open question from Angela Meyer, and they say, thank you to all presenters, thank you to judges and organizers. So thank you for being an attendee. All right, I'll wait a couple more minutes for any more questions. And if anybody has any parting words, I know we've got some new grad students that are going to be matriculating into their journeys coming this fall. That's extremely exciting, and congratulations officially.
Yeah, I have a thought. If you would have told me that you all were just getting started, for the folks who are entering grad school, I would not have believed you because everyone seemed so like knowledgeable and passionate about your work. And I just think that you should be really proud of yourselves because everyone did an excellent job at framing the type of work and understanding like the problem and the process for solving it. And I think that's a really hard thing to do. So you should feel really proud of yourselves.
I completely agree. My jaw's been on the floor since earlier today with the undergraduates. Everett, I saw you put your hand up.
No, that was me trying to react, but I forgot how.
All good. It's all
So I guess
good.
the hand up is just, raising you all up.
Right. Woo woo. I agree. Happy Juneteenth, everybody, too. And we do have some really sweet comments in the Q&A chat that I'll just share. Cheyenne Smith says, thank you so much. This was brilliant, encouraging, and inspiring. We need a podcast. Cosign. Anonymous attendee says, you guys are awesome. I'm glad I'm witnessing this showcase for the first time. We're glad to have you. Ashley Walker says, congrats to Dr. Bryant. Congrats. And I concur, Dr. Payne. So thank you all. I guess I will
Thank you
give
so
you guys
much.
the last. Oh, thank you. I think this was excellent. I will give you all the last 12 minutes of the session back. And we hope to see you for the rest of our programming throughout the week for Black in Astro and Black Space Week 2024, and stay in touch for future programming throughout the year. Thank you very much.
Thank you so much, everyone.
All right, thanks everyone.
Thanks, everybody.
Thank you so much.
Thank you.
You.